I wanted to show you guys how to get the formula for the Fibonacci sequence. So have a look right here. First off, let me just spell this out for you guys. Fibonacci sequence. And you know, every time like you have a word that ends with like chi sound, I think it's pretty cool. For example, the best example is Gucci, you know? So this right here sounds pretty fancy. Okay, anyway, Fibonacci sequence. So let me just tell you guys what it is first. Well, if you look at the numbers, it's just that we started with 1, and then the next number is also 1, and then to get the next number, we are just going to add them up. So we have 2, and the next we just add the previous 2 numbers together, and we will have 3, and then we will have 5, and then 8, and then 13, and so on, so on, so on. Okay, now the question is, what if we want to go on, and let's say we want to get to the 100th Fibonacci sequence number? Well, this is the first one, the second one, and so on. You can just keep going, just keep adding, but of course that will take too long. So let's see how we can come with a formula. Before we come up with an explicit formula for that, we will have to talk about the recursive formula first. And in order to make our life easier, I'm actually going to kind of backtrack a little bit. So what plus 1 will be 1? Of course, 0. So we can say this is like the zeros term. It will be easier that way. So I'm going to define f0, and the reason that we're using f is of course Fibonacci sequence. So we have f of 0 is equal to 0, and then the next number, that will be f1, and that will be 1. And then to get to the other numbers, we'll just say fn. This right here will be defined as the previous term, which is f sub n minus 1 plus f sub meaning subscript n minus 2. And this is only good if n is greater than or equal to 2. So now, how do we solve this kind of the so-called recursive formula or recursion? Let me introduce you guys this method, all right? Generally speaking, if you have a formula, let's say an is equal to 3 times its previous term, let's say an minus 1, okay? So this is an example of a recursive formula. You just keep multiply by 3. And remember, if you keep multiply by 3, that means that you have an exponential sequence, like 3 to the n, or namely geometric sequence. And maybe you have a number in front, right? Depending on the starting value. So that's just like the basic idea, but I will tell you guys the general form for this right here. If we have this, especially we are dealing with the previous term and also the previous term, this is an example of what we call the linear second order linear recursion. Then the general form is going to be fn equals some r value, and I will call that to be r1 because we will have 2 r's. r1 to the nth power. So it's similar to this idea that I just mentioned, but we have another part, right? So we are going to add r2 and then to the nth power. And again, we may have some coefficient in the front, so I would just say we have alpha 1 times that and then alpha 2 times that. So that's the general form. And now the main question is, how do we find out what R1 and R2? Well, here's the deal. We are going to start with the general form. I'm just going to say let fn be r to some power n, right, to the nth power. And then you see that here we have fn minus 1. So this right here is just fn minus 1. That means we have r to the n minus 1 power, and then fn minus 2 is just r to the n minus 2 power. These are our ingredients. We can just put them right here, and we will be able to find out what r is. So let's see, we will have r to the n being equal to, put this right there, we have r to the n minus 1, and then we add r to the n minus 2. And of course, notice this right here. R shouldn't be 0 because otherwise it's just 0. It doesn't make sense and you cannot produce anything from here. Okay, because r is not equal to 0, r to the n is also not equal to 0, so you can divide everybody by r to the n. And perhaps I'll just show you guys the work right here real quick. Divide everybody by r to the n. So that will give us 1 being equal to, cancel this out, we will still have r to the negative 1 and then plus r to the negative 2. Look at this equation and let's multiply everybody by r squared, and we will end up r squared, and this times this is r, on the right hand side, but let's put it to the left hand side. So we get minus r. This time this is 1, but again put it on the left hand side. So we have minus 1, and that's equal to 0. Have a look. We have a quadratic equation. And let me see. Yeah, I think we're good. So yeah, this right here is the golden quadratic equation because it will give you the golden ratio. And then of course you can solve it whichever way that you would like. I will just tell you r is equal to negative 1, which is positive 1, and then plus or minus square root of this thing square, which is 1, and then minus 4 times this and that becomes 1 plus 4, so you have 5 inside, and then all over 2 times a, which is just 2. All right, and right here we can say r1 equals 1 plus square root of 5 over 2. This is the golden ratio, which is approximately 1.618, like that. And then r2 is equal to 1 minus square root of 5 over 2. Okay, in fact, this is so interesting because if you just keep on going, pick any number and then you divide it by its previous number, let me tell you, you will get the golden ratio. If you do 8 divided by 5, you get 1.6 already. This number golden ratio is approximately 1.618. Alright, but we're not done yet because we still have to find out what alpha 1, alpha 2s are. But now we have the base, and then we have these two initial conditions, so we will be able to find them out, so don't worry. Alright, so next, let me just come back here. We know f0 is equal to 0, so I can say right here, f0 is equal to 0. This means I want to put the 0 into the end, so I'll just put it here, and we will have alpha 1 times. This is so nice because we have the 0's power. So right here, and then alpha 2, and then times 1 minus square root of 5 over 2, and then raised to the 0's power. So that's just 1, and we can move the alpha 2 to the other side. This means alpha 1 is equal to negative alpha 2, or alpha 2 is equal to negative alpha 1, one way or the other. Next, f1, well, that's equal to 1. So we can just say, put the n is equal to 1 into the n here and here. So we will get alpha 1 times 1 plus square root of 5 over 2, and then raised to the first power. And because we know alpha 2 is just negative alpha 1, so I will just say negative alpha 1. And then we will have 1 minus square root of 5 over 2, and then to the first power. Okay, this is actually not bad to solve. Here we have 1. Both of them have alpha 1, so we can factor that out. And then they are just to the first power, so nice. So we can do this. And then we can just put down 1 plus square root of 5, and then minus, and then we have this right here is 1 minus square root of 5. Yeah? And you see, 1 minus 1, it's just 0. And then square root of 5 minus negative square root of 5. So we have the alpha 1 here, and then times 2 square root of 5 over 2. And then of course we can cancel this out. Have a look. 1 is equal to alpha 1 times square root of 5. We can divide the square root of 5 on both sides. So alpha 1 equals square root of 5 on the bottom here, and then we have 1. And then this will tell us alpha 2 equals negative 1 over square root of 5. And we're done. Of course, lastly, I will just write down everything for you guys. Alright, ladies and gentlemen, this right here is the formula for the nth term of the Fibonacci sequence. So now we can be really happy, huh? Because now if you want me to find out the 100th term of the Fibonacci sequence, we can just happily put in 100 into the n here and n here. Do you really think so? It's true, but how do we compute 1 plus square root of 5 over 2 to the 100th power and do all the computation? I'm going to leave that to you guys, and maybe you guys can tell me what the 100th term is. But hopefully you guys all enjoyed this video, and it's so cool, I will say. Yeah, check out my next video. I'll see you guys over there though.